All right, good afternoon. Everyone, welcome to Science for Everyone. And today we're going to take a look and see if it's possible for Janelia to become carbon neutral. So, carbon neutral is a pretty new word. It was the word of the year in 2006, and pretty soon you saw it seeing in the headlines like this: can Hillary Clinton make her 2016 bid carbon neutral? So what does that even mean, to make something carbon neutral? So what we'll look at today is, what is carbon neutrality? Is it important? How can one become carbon neutral? How much does it cost? And what's the future for it? Is it a fad, or is it something that's going to persist? So carbon is found in almost every science. Every science you'll find uses carbon. And if you ask an astronomer about carbon, what they'll tell you is, in the Big Bang, when the universe started, there was hardly any carbon at all. And carbon is made in stars when they burn. And the first stars that were there burned and generated carbon. And if they're small, they blew up in planetary nebulas like this. If they're big, they blow up in supernovas. But they fling their carbon out into space in the form of little grains of dust. And then when later stars form, like the sun, they collect this dust. It forms a big disk called an accretion disk. And from this disk comes the planets. And so all the carbon that's in the Earth, and you and me and everywhere else, was once in the inside of a star, an earlier star in our galaxy. And carbon comes in a lot of forms. Pure carbon comes in two forms you've probably seen: diamonds and graphite, and three forms that are mostly, at the moment, seen in laboratories. And one of them is buckyballs. It's a little soccer ball-shaped carbon molecule. One of them is carbon nanotubes, like this. And the other is graphene, which is a single atom thick sheet of carbon. And all these have very spectacular properties. Diamond, of course, is extremely hard. Nanotubes are the strongest substance known for their weight. And graphene conducts electricity very well. And it's a good chance that graphene will eventually supplant silicon as the material for all our chips, if they can figure out how to make that work. And so that's pure carbon. Now, if you talk to chemists, you get a very different picture of carbon. Carbon loves to form compounds with different things, and it very easily connects and disconnects from other atoms. And in fact, the entire field of organic chemistry, which is probably most of chemistry that exists, is the chemistry of substances that have carbon in them. And it's so common that when they draw a picture like this of a molecule, they don't even show the carbons. There's a carbon every place where two lines meet, like this. So you can see there's a lot of carbons there. If you look at the one on the far side, you can see how many carbons are actually in that molecule. It's actually the main content of the molecule. And of course, you can see this can be used for either good or evil, right? The good chemists build products that are in high demand, and they use the capitalist system to make a lot of money on it. And the bad chemists, you see here, use the estate of dead billionaires to make chemicals that are used in small quantities by specialists, and often are toxic to the cells they're forcibly injected into. So you have to watch which chemists are good and which ones are bad. Now, in biology, almost everything we do in biology has carbon in it. And you see here's biochemistry. Well, cells, they get their energy from sugars, starches, and carbohydrates. All those have carbon in them. They store their energy in lipids and fats. All those have carbon in them. They build their structure out of proteins and amino acids. Those have carbon. And they store their data in DNA and RNA, also which are carbon-based, a carbon chain down the end of the atom. And so carbon's used in all biology as well. And the net result is, at least on Earth, carbon is completely ubiquitous. It occurs almost everywhere. So every plant is full of carbon. Every insect, every higher animal, almost everything we manufacture. There are some things you can find that don't have carbon, but it's tough. It's underground in the form of oil and coal. And it's in the air in the form of carbon dioxide and methane. And all these forms of carbon, because carbon is so reactive, can be turned from one to the other. And that leads to something called the carbon cycle. And what happens in the world is you have all this carbon, and it's in all sorts of different forms. It's in the atmosphere. It's underground in fossil fuels. There's a lot in the ocean, and there's a lot in plants, and it's all constantly switching back from one form to another. If you look at the diagram here, the arrow shows which way it's changing. But plants, for example, take carbon out of the atmosphere to make their own food, their own sugars. Then, when they die, they drop their leaves and everything onto the floor. Some of those decompose and release their carbon again. Some of them get buried and maybe become fossil fuels later. some of them get stuck in the soil. Likewise, the ocean absorbs carbon dioxide from the atmosphere and gives a lot back. And the fossil fuels represent all the carbon from long ago that's buried underground. Now, the part we're interested in today is this part right over here. Because what you see is that humans are digging up the carbon that's underground, burning it, making CO2, and putting it in the atmosphere. And you can see it's a pretty sizable contribution. In the atmosphere, there's 750 gigatons of carbon, and we're putting about 7.7 in it every year. So we're adding about 1% per year to the carbon that's already there. Now, that doesn't mean it'll go up 1% a year, because as the carbon goes up, some of these other processes get more efficient. But we're definitely making a significant contribution to the carbon budget. And if you look at it, what you see is that carbon dioxide has been in equilibrium for a long time. This is almost the last million years. On this chart, here's time before the present, 800,000 years ago till now. And this is the amount of carbon dioxide in the atmosphere. And you can see it's stayed between about 180 and about 300 at max over that time. Now, you might ask how they know this. What they do to find this out, they go to Antarctica, where the snow has been around for a long time. They dig a several mile deep hole. They take the ice out, and they look for layers caused by pollen and stuff so they can date it to the year. Then they look for little bubbles in the layers, and they go look at the gas trapped in that bubble, and they figure out what the atmosphere looked like 500,000 years ago. That's pretty cool. But anyway, they have this data going back almost 1 million years, because that's how thick the ice is in Antarctica. Now, recently, that carbon dioxide number has been going up. You see here, this is from about 1750 to modern times. Here's the Industrial Revolution here. You can see as we started to burn oil and coal, the number started to going up. And recently, it's been going up faster. And in modern technology, it's been measured pretty well. And it looks like this. This is the concentration of carbon dioxide in Hawaii. And you can see that every year, it goes up a little bit. It goes up and down, because in the summer, it's growing season in the northern hemisphere, and the plants are sucking carbon out of the air. In the winter, the plants die and release some back, and also we're heating our houses and things, and it goes up. And every year, it goes up a little more than it went down. And so as a net result, we're now about 400 parts per million of carbon, which is more than it's been in the last couple 100,000 years. And this carbon has an effect. This is something called the greenhouse effect. And the greenhouse effect is what sets the temperature of the Earth. The Earth is warmed by the sun. The sun emits energy mostly in the visible region and comes down through the atmosphere, and it heats up the Earth, like you stand outside on a sunny day. The Earth can only get rid of its energy also by radiation, but it's much colder than the sun. And so it radiates not in the visible, but in the infrared. The infrared is what you get when you sit underneath one of these outdoor heaters. It doesn't give you a lot of light, but it feels warm. That's because it's giving off infrared radiation. It's getting rid of heat. And so it's the same thing here. So what happens is, with little CO2, the sun provides the energy in, it warms the Earth, and the Earth gives that energy out, and that equilibrium sets the temperature of the Earth. Now, when you add CO2 or any other greenhouse gas, these gases are transparent in the visible, but they're opaque in the infrared. And so what happens is the same amount of light still comes in from the sun, same amount of energy comes in, it goes out by radiation again, but it gets absorbed by this layer. It's like a layer of clouds for infrared. Now the clouds then emit it again, but only half goes out. The other half goes down because they're not emitting it directionally. And so the Earth is warmer than it would be if you didn't have these gases in the atmosphere. And so the calculation is complicated because you can also get clouds and aerosols and all sorts of other stuff, but that's the basic idea. And we know it's pretty much true because we can look at our neighboring planet Venus. Venus, right? It's a little closer to the sun than the Earth is, so it gets 92% more sunlight. And if you work out the numbers, you say if it had the same atmosphere as the Earth, the exact same atmosphere that we have, it'd be about 50 degrees centigrade hotter, about 90 degrees Fahrenheit. And so it would be hot, like 130, 140 degrees Fahrenheit or 60 degrees centigrade. It would be too hot for us to live, but not ridiculous. But if you actually measure it, what you see is it's 460 degrees centigrade or 860 degrees Fahrenheit. That's hotter than a self-cleaning oven. It's hot enough to melt lead. Now, it's got the same sun as we do, so why does it get so hot? It gets that hot because of this effect with the carbon dioxide. It's got an almost pure carbon dioxide atmosphere, and it keeps the heat in that tries to escape, and it warms itself up. And so this is not at least in high concentrations, it's not a theoretical effect. So now, people are also pretty aware that the temperature on the Earth has been increasing. And so they've been measuring this, and people argue over whether that's a flat spot over here or whatever, but still on the whole, you can see over the last century, the temperature has been going up. And if you plot carbon dioxide along with the temperature, you say, huh, these curves look pretty similar. Is that a coincidence or not? Now, just because two curves look the same doesn't really mean that one causes the other. There's a great example of that, which is this. Here's two curves that look the same. They're going up just like temperature and everything else. And one is the incidence of autism, and the other is sales of organic food. But people don't think this is, people think this one's coincidence, unlike climate change, because there's no mechanism. No one has any way that one of these could cause the other, right? That unless autistic people eat a lot of organic food or something, but there doesn't seem to be any evidence for this. Yes, sure. It could be, but people have looked at this. If you're interested in this, there's a whole website called spuriouscorrelations.org where they measure all sorts of weird things like this. My favorite one is the number of people who die from poisonous spiders in the United States almost perfectly correlates with the length of the word that won the spelling bee in that particular year. It's almost perfect correlation. And so maybe the spiders read, I don't know. But anyway, the curve that we showed for carbon dioxide, we think this is real. We don't think that's a spurious correlation because there is a mechanism and people can work out the numbers. The numbers for carbon in the atmosphere are pretty solid, and you can see the data is pretty stable. The temperature is much harder. The temperature goes up and down a lot by itself, and you have to take averages, and there's problems with clouds and aerosols and volcanoes and all sorts of other influences. But still, people are pretty convinced this is the case. So now you can define carbon neutral. You say, well, we don't want the temperature to go up, so we shouldn't emit more carbon. And so whatever we should do, whatever I do that emits carbon, I should make sure that it doesn't make this global temperature problem any worse. And so the way to say that is we don't add any net carbon to the atmosphere. Now, in theory, that's very easy, right? You just stop burning coal and oil, and you would get back to the natural stable state. But that's politically impossible because people like us, we like air conditioning, and we like central heating, and we like to do research, and we like to drive our cars, and things like this. So it's very unlikely we'll stop using fossil fuels. And furthermore, the 4 or 5 billion people who don't have this very justifiably want it, right? They say, hey, wait a minute. You people got the benefit of all this stuff. We would like to have the same conveniences that you have. And so the only way you can get to this point where everyone can have a good standard of living and not cook the earth is if the processes become more carbon neutral. So how do you become carbon neutral? Well, you can say, well, the carbon neutral comes when you consume energy in general. And so here we have a plant by Dominion Power. That's where we get our power from, running Janelia. So maybe you can get your power from somewhere else. So get rid of that and instead put in a nuclear plant, right? That doesn't generate any carbon dioxide, or solar, or wind. All of those are very good in terms of the carbon dioxide that they generate. Alternatively, you can get rid of the carbon dioxide you generate. So in this case, Janelia uses the power. That causes Dominion to emit carbon dioxide. But we could, for example, plant trees to consume an equal amount of carbon dioxide. That brings the balance down, and once again, you're neutral. Or we can offset CO2. And this is the same idea as the trees, except it's worldwide. Because remember, we don't care about where the carbon comes from or goes. We just care how much there is across the whole world. And so here we could take some place that's already emitting carbon dioxide, say from a power plant, and we add Janelia over here, and that causes Dominion to emit even more carbon dioxide. However, now we can build a solar panel, maybe not here, but somewhere else, and that causes that one to reduce its power requirements, and now you're down to the same 2 units you had at the beginning. And so you can offset your carbon that you make here by a reduction somewhere else. And in particular, that may be easier because somewhere that's generating their power with coal is using a lot of carbon to generate that. So it all boils down to cost. Right? Everyone agrees that carbon dioxide should be limited. And if it's in their own interest to do it, they'll do it. If it looks like it costs money, then people are always finding excuses to not do anything about it. And so the first step is to estimate the cost. So what about Janelia? Well, Janelia, I mean, you obviously know where it is. It's scientific research. We have 380 researchers here. According to Danny, who you see, we have about 910 people who work on campus. That's because you need security and human resources and facilities and all sorts of stuff to actually keep the researchers in business. And where does our energy go? And I'm going to give you 3 options, right? Now, one thing we have here is a big data center. This is a couple thousand computers that run 24 hours a day that use energy. So keep that one in mind. Another thing we do is we have a lot of lab equipment. If you go in any of the halls upstairs, you see they have these just rows and rows and rows of refrigerators. And you think that at home, your refrigerator is one of the bigger uses. And these refrigerators are kept at minus 80 degrees C. And so these guys take a lot of power. And the third one is the traditional heating and cooling. And so now I'd like to see a show of hands on who thinks which one is the biggest use. So how many are going to vote for data center? 1, 2, 2, 3. All right, 4, 4. How many vote for lab equipment? Maybe 5 or 6. And how many vote for heating and cooling? Whoop. Frantically raising your hand. Yeah. And that's completely correct. It's heating and cooling. And you can tell that just by looking at Janelia's energy curve. So you look here, this is months of the year. This is how much energy we use, both the green curve in natural gas and the blue curve in electricity. And just like you expect, you see the natural gas is high in the winter when you're heating the building, and the blue curve is high in the summer when you're trying to keep it cool. And so our research is pretty flat, somewhere down here, less than 1 million total. And so by far, the biggest fraction of the energy we use goes towards heating and cooling the building. Now, you might think, yes, sure. This is all converted to kilowatt hours. It's kilowatt hours, I believe. I'd have to check the, yeah. We use 4 megawatts, right? So we're going to use a kilowatt hour every second or so. Those are appropriate numbers. So you might think, of course it's expensive. It's all this glass, right? We've got a huge amount of glass here, but the glass is actually pretty good. If you talk to Mark, you'll find out the glass is not our problem. The problem is, at least in the summer, the old saying, it's not the heat, it's the humidity. You heard that? It's actually true. So what happens is, we have to keep the building at a reasonable humidity level. We try to keep it at 50%. And that's not for your comfort. No one cares whether the employees are comfortable. But the animals you're required to keep the humidity between 30 and 70%. It's a legal requirement. And so that can get difficult when you get a Virginia day in the summer and the weather is hot and it's humid. So what this curve shows, this on the bottom is temperature here. In Fahrenheit, these are some numbers in centigrade here. And the y-axis shows how much water the air can hold. And what you can see is the temperature goes up, the air holds a lot more water. And you see on an 85-degree day, this is 60% humidity, this is how much water the air holds. And what you want is 70 degrees and 50%, which is that much water. And so what will happen if you just cool the air, if you just ran your air conditioner like this, what happens is you cool it down to 70 degrees, but now it's 100% humid, right? Because you haven't got rid of any of the water that's in it. And so you can't do this. So what you have to do instead is you cool it down farther. You cool it down to about 53 or so, somewhere in there. At that level, the air can't hold as much water here. The water drips out. This is just what you see, you park your car when the air conditioner's on and the water drips out. That's exactly this. That's what's happening. And you drop it down to 50 degrees, and now you heat it back up, which doesn't affect the water, and you get this. So now you're where you want to be, 70 degrees and 50%. But it took a lot of energy to do that. Now, why does it take so much energy? It's due to something called latent heat. Now, latent heat is something that everyone knows. You probably don't know the name unless you remember your thermodynamics, which is pretty unlikely. But you can imagine it. You want to boil something on the stove. So you put your pot on the burner, and you turn on the burner, and it heats up, and in a few minutes you got it up to boiling. And so you put in a few minutes worth of heat, and you raised it from, say, 10 degrees C to 100 degrees C, and that's called sensible heat, because you're adding heat to the system and the temperature is changing. But now, say you try to boil that water off, right? That'll take you even longer than it did to get it to boiling in the first place. And it's not changing the temperature at all. You're turning water at the boiling point, 100 degrees C, into steam at exactly the same temperature. So you're not changing the temperature. But it took a lot of energy to do that. And that's called latent heat. That's what it takes to take liquid water and turn it into vapor water. Now, when you do air conditioning, you got to do exactly the opposite. You got all this energy that's stored in the hot, humid air, and to turn it back into water, you have to suck all that energy out. And so, according to Mark, he says this step here, where you suck the water out of the air, on a hot, humid day in Virginia takes twice as much energy as actually cooling the air does. So to get 1,000 watts of cooling power, you need 3,000 watts of energy coming in. And so that's one of the reasons why it's bad to live in a hot, humid place like Virginia. So, all right. Another reason why we take a lot of energy here is special requirements for laboratories. This is the flow of air conditioning in a regular office building. And so what happens is the air comes in from outside. It's mixed with the air that's already in the building. They heat it and cool it and dehumidify it, everything they need to do. They run it into the offices. And when it's done in the offices, they take maybe 3/4 of it and recycle it. 1/4 goes out and is replaced by outside air that's moved in. And that makes a lot of sense because you spend a lot of energy taking that outside air and dehumidifying it and cooling it or heating it or whatever you needed to do. But in some cases, you can't do that. In particular, in laboratories, if you have a laboratory, if that room contains chemicals that can be volatile, like all the labs on the 3rd floor, for example, then you're not allowed to recycle it. So you can't do that. So you have to do all this work to heat and cool the air, and then you throw it out. And so, as you can imagine, right, if you can't recycle 3/4 of it, instead you have to throw it away, that's a huge extra budget. Similar things need to be done for vivariums. There's only so much recycling you can do when you have animals there as well. So we have some special requirements. About 20% of all of Janelia, in fact, has these requirements. Okay? And so now with that, we can calculate Janelia's carbon footprint, which is carbon footprint is just how much carbon something takes. And 3 sources: electricity, natural gas, and travel by employees. And we'll look at each in turn. Now, for electricity, you can't tell by how much electricity you use how much carbon dioxide, because it depends on how that electricity was made. If you make it from coal, every kilowatt hour puts about 950 grams in the atmosphere. If you make it from natural gas, it's much better, because now in addition to burning the carbon, you're also burning the hydrogen to make water, which is okay. And so it's not quite twice as good, but it's pretty close. Oil somewhere in the middle between coal and natural gas. Now, nuclear, solar, wind, biomass, all these things, they don't take any carbon when they're running. It's not like a coal-fired plant. They don't take carbon while they're operating, but they still have some carbon budget because they had to be built, right? Energy went into building them, energy goes into running them, and energy goes into decommissioning when they're done. And so people have studied that a lot because people are justifiably worried that maybe you have a solar cell and it takes more energy to make the cell than you ever get out in its lifetime. But it turns out that's not true. If you work out the numbers, the lifetime carbon cost per kilowatt hour is between 4 and 40 grams for all these different alternative ones. And that's less than a 10% of the best of the fossil fuels. And so it is a worry, but it's not that bad. And furthermore, you also have these for the other ones too. I mean, the conventional plant had to be built as well. It's just that for the conventional plant, it's completely dwarfed by the operating costs, so people don't look at it. Yeah, sure.
Does that include the geographic variability of the net output energy from the solar in Germany in the winter?
No, that's the offset. What they do for this is they take how much energy it takes to build the windmill or the solar panel or whatever, and then they look at on the average how much energy they get out. They don't look at what they're offsetting, whether it's offsetting coal or whatever. This is only looking to say, how much. Well, I guess it would, right? If you manufactured the solar plants in a coal-burning facility, then this number would be higher. I think for this one, what they did is they looked at a number of them and how they're actually built and where they're actually used to get these averages. But since it's an order of magnitude different, it probably would still be better than fossil fuels. Okay. So now, what about our electricity? Well, we get our electricity from Dominion Power. Probably if you own a house here, you probably also get your electricity from Dominion Power. And this is where it comes from. It covers 4 states: North Carolina, Virginia, West Virginia, and Maryland. And they generate their electricity 41% from nuclear, 37% from coal, 18% from natural gas, and 3% from renewables. So the renewables is pretty slim pickings at the moment. And therefore, you can look at it and say, a kilowatt hour here, how much carbon does it make? Now, Dominion over the years has been improving a lot. It used to be that every kilowatt hour generated 600 grams, and now it's down to 350 grams. And that's not bad, because if you look at coal, that's where coal would be. If you were generating it from coal, like they do in West Virginia, that's what your number would be. So it's not so bad. Now you say, why is it getting better like this? I guess Dominion must be really environmentally responsible, and that's completely false. The reason that they're doing this is because it's cheaper. right? That because they have fracking now, fracking generates natural gas at very good prices. And so people are taking their coal-fired plants and turning them into natural gas plants just because it saves them money. And so, this is a sort of interesting thing, because environmentalists, sometimes they oppose nuclear power, sometimes they oppose fracking, sometimes they oppose regular fossil fuels, but all these things have trade-offs, right? That nuclear may have a problem with accidents that kill millions of people, but that may not be so bad, because sea level rise could kill billions of people, right? Or certainly inconvenience them if they have to move. And so you have to take these trade-offs between the different drawbacks and advantages of the different technologies. In fact, you could easily argue that what we should do, the best thing we could do for global greenhouse warming, is to export as much fracking technology as we can to China for free, right? And that would be good, because they're building huge numbers of coal facilities because that's what they have. Okay. Natural gas, that's easy to figure out, right? It's basically methane. It's measured in these weird units. You look at this, you get these weird units. You get like a therm is 100,000 BTUs. Now, why'd they pick that? I have no idea. What's a BTU? That's the amount of energy required to change 1 pound of water by 1 degree F. So it's sort of like the antique version of a calorie, which is 1 kilo of water, 1 degree C. So anyway, they have all these weird numbers. So you work it out. You can add up that. And then you have to look at travel. Now, how much travel does Janelia do? And I made an estimate a couple different ways. A modern plane takes about 100 grams, generates about 100 grams of CO2 to transport 1 passenger 1 kilometer. And so now you can make a guess. You say, well, if you're a lab head, maybe every year you make 1 trip to Asia, 1 trip to Europe, and 2 trips domestically. And add it up, that's 3,600 kilograms of carbon for your trips. And you say, well, maybe 200 people do that amount of travel. Actually, some of them do less, some of them do more. But that would be sort of a guess. You'd end up with 720,000 kilograms. Now, I did the same thing another way, which is I went to Jerry and asked, how much do we spend on air travel? And he says, 600K. You say, okay, if it costs you 1,000 for a trip to Europe and 500 for a domestic trip, you end up with almost exactly the same numbers. It's just a little bit different, 600K instead of 700. But for this kind of accuracy, that's a perfect match. And so you can say, that's about how much we spend. Now you come to conferences, right? We host a lot of conferences here. According to Janine, we have about 20 conferences every year. And for each conference, about 50 people will come here by air. And so that's 1,000 trips. So that's comparable to the amount of travel that all the people at Janelia do during the whole year. But now you have the question of whose budget should that count against? Because say you're a professor at Berkeley, and you come here for a conference, right? So you made a trip across country, you used up this carbon. Should that count on Berkeley's carbon budget? Because that's where the professor works? Or should it count on our carbon budget because we invited them and maybe paid for their travel? Not in that case, but in other cases we would pay for the travel. And so these questions of how you allocate these things are also sometimes contentious. And so if you look at the overall pie chart, this is where Janelia's carbon budget goes. Most of it goes for electricity. The next chunk is for natural gas. And a pretty small chunk is for travel. Now, this is without the conferences, but if you completely included all the conferences, you about double the size of the green. It's still not a big contribution. And so total, it's about 22,000 tons per year of carbon dioxide, or 24 tons per employee per year. So that's how much we make. Now, what can we do about this? We have a total amount of carbon dioxide. We can actually pay someone. You can buy carbon offsets on the market. And so you pay some money to someone who collects all that money together and builds a solar farm or a windmill farm or something in some region that's otherwise using fossil fuels and gets rid of carbon that way. And so when you do that, you pay something like $10 to $30 per ton of carbon removed. And so that would cost us somewhere between 200 and 600K per year to get rid of all the carbon we create. So, but that's, of course, several researchers and our travel budget and a bunch of other things. So no one is really keen to do that unless you have to. Another way would be to absorb by growing plants. And finally, another way is to generate our power another way. We could build our own nuclear reactor. There's probably a lot of paperwork involved with that. Go solar, wind, or biomass. So removing the CO2 from the air is the most straightforward way. According to the American Forest Association, an acre of forest removes 186 metric tons of carbon per year. I told you about these weird units, right? Tons per acre per year. That's a sort of weird unit. And so to absorb that much carbon, you need 118 acres of trees, or about a half square kilometer. Now, you also, question? Sure. No, that's the next thing here, right? You have to worry about what the trees when they're grown, right? Because you can't burn them, right? That would do no good at all, right? So you have to figure out, you have to like take the trees and bury them or use them as lumber in some place that won't go or whatever. So you have to worry about this. But it's good for 20 or 30 years. And then you have to replant new trees. And yeah, if you burn them for energy, that wouldn't be so bad. Right? But then you're using neutral for that energy, but then you're not offsetting any of Janelia's energy if you're doing that. Well, I guess you could do some, right? Now Canada was looking into this big time because Canada has oil sands. And oil sands are like the most carbon producing thing you could possibly imagine, refining them into gasoline. And so they looked at planting forests and they concluded it would cost $1,200 a hectare. A hectare is like 2 acres. And if that's the right cost, that's not bad, right? That means you could plant a half a kilometer of trees for about 60K. So that's not a bad technique for getting rid of carbon. No. How about generating electricity, right? If we built solar power here, that would allow Dominion to generate less. And so Dominion is not going to turn off their nuclear plant because they use that full capacity all the time. And so the marginal amount of carbon reduced would be that of gas or coal. So let's say 700 grams a kilowatt hour. That means to offset all of the carbon that Janelia uses, natural gas and electricity, we would have to generate 31,000 megawatt hours per year, which is 86 megawatt hours a day. Now, to do that, you have to figure out how big your solar panels would have to be. And to do that, you have to look up the sun in various places in the United States. And you can see here in Washington, D.C., we get, over the course of a year, an average of 4 hours of sun per day. Not quite as good as LA or Miami, but much better than Chicago or Pittsburgh, for example. So we're sort of in the middle in terms of our solar requirements. We would need about 86 megawatt hours a day, which means we would need about a 20 megawatt solar farm to do that. Now, you can do that. In fact, it's quite popular in North Carolina. And the reason is that North Carolina has a lot of data centers. And a lot of the companies want to at least seem environmentally conscious. And so they're putting in solar power with their data centers. This is Apple's. There's the data center. There's their solar array right there. And that's just about the size we would need, 20 megawatts. At 2.5, I didn't count that. It's a serious question. Yeah, no, it's a serious question, right? This is exactly the same size as the forest you'd have to grow to get rid of the same amount of carbon, as it turns out. Right? So it's a serious question. Now it costs you $50 million, but you get some money back because now you've got more electricity than we're using. Because remember, you're trying to get rid of the natural gas carbon too, and so you sell it back and you save about $2.5 million. That means at current cost, that's a 20-year payback. Now that's not enough for Janelia, because Janelia is funded by HHMI, of course, and HHMI by law has to spend 5% of their total endowment on operating expenses. And what that means, if you spent $50 million there and you get $2.5 million back, you're just barely treading water. So this would actually cause our endowment at most to stay even. And so this is not something we would invest in with a 20-year payback. Now we can check these estimates. If you've ever gone north, if you drive north on 15, you go through Mount St. Mary's, a university right in the north of Maryland. And they did exactly this. They did exactly what we're saying here. They decided to offset their carbon. They built a set of solar panels here. There's a 16 megawatts, close enough to 20 for this. And sure enough, it cost $50 million, takes 100 acres, or 0.4 square kilometers. So it's definitely possible. These exist in North Carolina. They exist in Maryland. We could build it here. Okay. Now, how big is this? This is the Google map of Selden's Island. You've seen, here's the landscape building here. Here's Selden's Island. And what I did is I took this contour here and went around the part that's cleared. Because remember, Selden's Island used to be a sod farm. And so this part doesn't have any trees on it. So you could grow trees and have a net absorption of carbon. If you look at the total area, it's about 1.5 square kilometers. And so if you need 0.4, you need to cover a third of Selden Island with either trees or solar panels. And you could completely offset Janelia's carbon. Now this would be interesting because the reason you can't build there is it's in the floodplain. But the forests don't seem to mind. I mean, the other trees on the island don't mind. And so maybe this would be a possibility. Okay, how about wind? Now wind is a little better than solar. Solar, you get solar for an average 4 hours a day. So that means if it has a 100 kilowatt capacity, you only get a sixth of that, really, or if you average over a day, because it's only really on for 4 hours. Wind's better. You get 30% of what the wind turbine is rated. Hence, you need about a 15 megawatt wind farm, at least here. It would cost you about 30 million, so it's cheaper than the solar panels. It pays back quicker in 12 years, but it requires a much bigger area. The wind farms they have in Texas, they buy land from farmers and they set them up. You need about 7 square kilometers. So we couldn't do this here. You have to do it somewhere else. And it would make sense if you're going to do it, you would do it in West Virginia. Because if your goal is to get rid of carbon, it's much better to get rid of electricity that's made from coal than it is to get rid of electricity that's made from natural gas or nuclear or anything else. And so if you did this, if you did it in West Virginia, where the power generates 3 times as much carbon dioxide per unit power as here, you could use a much smaller array. It's still a 12-year payback. You get less money back too. Okay? So that's 3 solutions sort of in order of cost, right? You could plant Selden's Islands with trees. You could build a wind power farm in West Virginia or any other location where you're displacing coal. Or you could go with solar power, although that one is definitely not economically feasible right now. So that's for Janelia. Now what about the employees, right? There's a lot of employees here, and they use carbon. One of the ways they do carbon that's extremely hard to reduce is breathing, right? That each person here, every one of you, is generating at least a kilogram of carbon dioxide per day just by existing. And that's really hard to fix. And in fact, if you're exercising, it's worse. People who exercise generate like 2 to 3 kilograms of carbon per day. So don't exercise whatever else you might do, all right? So, but they also live in a house or an apartment. They drive a car, they take vacations. And I'll use myself as an example because I got the data for this. So, although I suspect I'm typical. Now, if you have Dominion Power, you can just log onto their website and see how much power you use. It'll give you a nice little chart just like this over the last year. How much did you use? And you can see that in our house, we don't have natural gas where I live. And so we have to use electricity for heat in the winter. And so what you see in our house is a bump in the summer from air conditioning here and a huge bump in the winter from heat. And that's with a heat pump, but they still don't work all that well in the winter. Next, of course, I drive a car. So an average driver drives 30 miles a day, 10,000 miles a year. I'm pretty much average, I think. That's about what I run, mostly running my son to and from soccer practice. But so, and that with an average car is about 4,500 kilograms of carbon dioxide per year. And take a vacation. Now, I used last year's vacation, which turned out to be really bad in terms of carbon, because what I did is I flew to England. That's like 1,000 kilograms of carbon right there, round trip, and went on a cruise. And cruises are run by diesel engines, and they use a lot of carbon, like 150 kilograms a day. Of course, this varies by ship, et cetera, but it's quite a bit. And so you add all that up, what you see is my carbon footprint looks very different than that of Janelia. This little purple heart here is what I generate by breathing. Right, so I can't do much about that. This is 1/4 of the house I live in. I'm assuming that the other people will have to pay for their quarter. The car is here, and vacation is here. Now, the biggest chunk is a car. And you might say, well, maybe I should switch to an electric car. Would that help? And you can easily tell that. So what you do is you look up these different electric cars, and they all have fuel mileage efficiencies that are the same as gas cars. They're just measured in miles per kilowatt hour instead of miles per gallon. And they're all sort of in the same general area. And so if you drive your 10,000 miles or 16,000 kilometers a year, you'll use up about 3,500 kilowatt hours, which generates, in Virginia, about 1,500 kilograms of carbon dioxide. So that's 3 times better, because the car itself was 4,500, but the electric car is only 3,500. Now, but that's because you live in Virginia, where they generate electricity by means of nuclear power and natural gas. If you lived in West Virginia, where they generate power by coal, it's pretty much a wash. In other words, the electric car is very efficient, but the turning coal into electricity is not very efficient. And so you don't really gain anything if you live in a place that builds their electricity by coal. Now, the obvious thing to do is charge your car with solar power. That gets you out of this problem. And it works out just about right. If you drive 30 miles a day, now you need 11 kilowatt hours. You get 4 hours of sun if you live around here. That means you need 2.5 kilowatts peak power times 4 hours is somewhere in that range, which means you need about 12.5 square meters of solar panel. So about like one of these things you see here. Now, interestingly enough, that's exactly the size of a parking place, right? A standard parking place is 2.5 meters wide by 5 meters long. It's also 12.5 square meters. And so if you just take an outdoor parking place and cover it with these shaded solar panels, like various places do, you can actually, on the average, generate enough power to run your electric car and reduce your carbon emissions to zero. And you see this a lot in California. In California, it's even the schools and things are putting in these solar shaded parking lots. Now, how could I become carbon neutral, right? Well, if I paid someone to offset the CO2 that I generate, it would be $100 to $300 a year. That's not ridiculous. I could plant trees. I'd have to plant a 1/20 of an acre of trees. I don't have a spot on my front lawn where I can put that many trees, so that doesn't work out very well. Or I can try to offset by producing clean power. Now, for me, I can't use wind power because I live in a region without an HOA, but still probably someone would object if I built one of these giant wind turbines in my backyard. And so how about solar? Well, if you look at it, you say, oh, you look at how much power you need, and you say, well, I need about 50 or 60 square meters to compensate for all the carbon that I produce, right? And now you look at the house, this is looking at the top from Google Maps, and you look at the roof size here, and the south-facing roof is 90 square meters. You say, okay, that could work. So at least I can get rid of my carbon by building solar panels on the roof. But the economics are not that good, right? That if you ask for a bid now, what you'll find for solar power here is it's about $4 a watt installed. Remember these big ones like Apple does? They're $2.50 a watt because they get a big economy of scale. You don't get that for these small projects like this. And so if you covered the roof with solar panels, the south-facing roof, what you find is it would cost you, generate 14 kilowatts, cost $56,000 to build it, but you get a big tax credit, 30% or something, so it's $40K after taxes. But it only saves about $1,700 a year in electricity because here, electricity is cheap. It's 8 cents a kilowatt hour, and there's no time of day metering or anything else. So you're not going to gain much. And so the payback period is quite long, right? It's not a good investment, at least at the moment. Okay, now what about vacation? Right? Is there any way you can reduce your carbon from vacation, assuming you still want to take the same vacation? And the answer is basically no. You can't keep the cruise companies from generating carbon because biofuel, which you might use for that, is more expensive than regular fuel. And so the companies being cost optimizing just don't use it. And in theory, someone could start a company that says, okay, we only use biofuel for our cruise ships. And if enough people bought it, then it could be an industry, but I don't think that would ever fly. The long-term fix, the only thing you can do right now is offset it. In other words, you have to, if you want to go on a vacation, you have to do something else that'll reduce some other form of carbon because you're not going to affect the cruise or the plane companies. The long-term fix might be a carbon tax to change that behavior, but that's extremely difficult politically. So my options are, for me, right, I can't plant trees because I don't really have the room. I don't have room for wind energy. So my options are two, right? I can purchase offsets if I want to be carbon neutral, or I can use solar power, which works technically, it's fine, but it still doesn't really pay for itself. So I would have to be a benevolent environmentalist in order to do that. So what's going to happen to this situation over the next couple years, right? In the short term, not much. It's going to be exactly the same things I described, just with better prices. The price of solar panels is coming down, the price of wind energy is going down, and so on. But in the long term, eventually you run into a limit. And that limit is when you have enough alternative power that you're not using any coal during, say, the day when the sun is shining. Then at that point, more solar panels don't help reduce carbon because there's no more carbon production to reduce during the day. And so I'll talk about that a little bit later. But there are countries that are seriously looking at this, like say Denmark is one. And they're doing it in sort of 3 steps. The first step is to be able to generate all the electricity for your country without using any carbon. Right? And the second one is get rid of the stationary applications because they're the easiest ones to fix. So if you're using natural gas to heat your house, you could use electricity, and that would get rid of CO2 if your electricity was also generated without carbon. And then the hard one, finally, is transportation. How do you get rid of the fuels used for transportation? There you have to switch to biofuels or offset or something else. But it's sort of a 3-step process. Now, there's 2 countries in the world that this year spent a couple months without using any fossil fuel to generate their electricity. Can anyone name what they are? 2 of them. Any guesses? Iceland. Okay, that's one. That's good. What's the other one? Costa Rica. Perfect. We've got a very good audience here. Those are the 2. And whoops, that's the lower cost. Costa Rica can do it because it's a mountainous country with rainforests. And so between mountains and lots of rain, they can generate a lot of electricity with hydropower. And in fact, they do. They went 75 days earlier this year without using any oil for their electricity. And Iceland can do it because they got a lot of geothermal energy. They dig wells, they run water through them to turn them into steam, and they drive their turbines that way. And that works great as long as you have lots of volcanoes. So these are two strategies that are not expandable, right? Not exportable to the United States. And people also say, oh, this is just little niche countries. Like, you can't do that with a real country that has a real economy, et cetera. But it turns out you can. This is Denmark. Denmark has a standard of living that's ours or better. And they've concentrated on wind. And you look at windy days, this is what they do. You look at they keep a real-time thing. You can log onto the internet and see this. But if you look here, for example, this is what they generated from wind turbines. And this is the total electrical demand in the country, right? So it's more than 100%. They're exporting power. And so on windy days, Denmark uses no fossil fuel. So it's definitely possible. And they say, well, but Denmark is a small country, right? Hamlet was the Prince of Denmark, no big deal. So how about a real country that makes real stuff, like, cars and things? So let's look at Germany. Now, Germany, being Germany, keeps super accurate track of where all their energy comes from. And here, for example, is a week this year. And this is the total amount of energy needed. It peaks every day in the middle of the day. It goes down at night, like that. On Fridays, people start to goof off. And on the weekend, it's quite a bit less, right here. And the three different colors here, the yellow is solar energy. This greenish one here is wind energy. And the bottom, the grayish one here, is fossil fuels. And what you can see is on days that are good, windy and sunny days, they produce a good fraction of their energy from renewable sources. And so that's the total energy you see there on one day. But if you look at that much comes from green, from renewable energy, and only that much, about 40%, comes from fossil fuels. Now, if we had the same thing here, we'd be zero fossil fuels because we generate about that black amount from nuclear. Now, Germany is against nuclear, and they're trying to phase it out. But nonetheless, if you were worried about carbon, it might not be a bad thing to do. So a country that's 80 million people, big economy, everything else, can get to the point where under good conditions, they're generating no carbon. Sure. Right. Right. I'll get to that in just a second, actually, because I'll talk about. So people say, well, that's a. Yeah. Right. Well, Carl was saying, well, the problem is the electricity here is just too cheap. It keeps people from doing this. But that's not true everywhere. If you look at Hawaii and California, where electricity is expensive, they are making real progress in terms of getting rid of fossil fuels and replacing them with energy. You look at this. This is in California, solar is possible. This is a curve over one day here. And it used to be the highest demand was right here in the middle of the day when the air conditioning is on. But you see right now, that's the least demand because in the middle of the day, all these solar panels are generating electricity and pushing the total amount that needs to be generated by fossil fuel down. And it's sufficient enough that by 2020, they think they may have negative production, right? That they may have, when you add in the nuclear plants, they actually have to get rid of energy to get rid of the energy they're making by the solar things. Likewise, Hawaii. Hawaii they have to import, of course, all their oil and all their natural gas and anything else they use. And they've decided, they passed a bill that said they're not going to build any more fossil fuel plants. Every new plant they build will be renewable. And at that rate, by 2050, they'll be 100% renewable power. So there are people that can do it, and it depends on the economy, just like Carl said. So there's a bunch of technical problems you can see on the horizon. One is storage, right? Right now, you don't need it because if you generate solar power during the day, you're taking away someone else's carbon power. Once that gets down to zero, and there's no carbon power left to remove, now you're not helping by building more solar power, unless you can store it. Also, if you want it to work at night, and when the wind isn't blowing and stuff, you need storage. And so that's one problem. Another one is transmission. It turns out the good places to generate this power is not where you want to use it. For example, solar power works great in the deserts of Arizona, but the place where you want it is in LA or Denver or other cities. And likewise, wind power is great on the prairies of the Midwest, but there's no big cities there. And so in order to be able to use this power, you have to build more transmission lines, and that's often a problem. Another problem is stability, right? Because these wind and the solar, they all fluctuate. Solar due to clouds, wind due to fluctuations, and you have to keep the grid stable despite these varying supplies. And then finally, one of the big questions is, what about long-distance transportation? Because that's one of the few things where you can't substitute electricity, right? There's no electric planes or electric trucks. Now, it turns out biofuel works well for that, right? People have tried all these things out. They've verified that they work. You can build biofuel trucks, works fine. You can build biofuel ships, that works great. You can build biofuel airplanes, that works great too. And so these are not technical problems. Why don't people use biofuel? It's very easy. This is a chart here. This is the last 5 years on this axis, and the cost of oil on this axis in dollars per barrel. And so what you see, and now in this rectangle here, is sort of the approximate cost of different kinds of biofuels. And so what you can see is when the price of the oil was high, the biofuels are competitive. But when the price of oil goes down, like it is now, there's no way, right? That biofuels are 2 or 3 times as expensive as the conventional fuels. And so this is the major reason why no one is adopting these for transportation. And so probably the only solution to this is either higher oil prices or a carbon tax or something else to try to equalize the field. But quite frankly, until people have gotten rid of the other sources, I don't see this as being a huge incentive. Because it sucks to generate the oil, it sucks the carbon dioxide out of the atmosphere, which is what the plants do. Then you turn that into oil, and then the same carbon dioxide gets emitted out. So minus the energy used for farming, you're not generating or removing any carbon dioxide. Right. Right. Well, I mean, it doesn't matter whether you grew it for the biofuel or you just took anything that grew. I mean, you can't take, well, how else would you get biofuel other than growing it? Mm-hmm. Right. Mm-hmm. Mm-hmm. Yeah, no. So the biofuel, it has to be made from stuff that's grown. That's absolutely right. If it's made from just junk you have lying around, it won't help. So anyway, in conclusion, so could Janelia go carbon neutral? Yes, they could. We outlined 3 ways, right? They could plant Selden's Island with trees. They could build a wind farm, or they could build a solar thing. Can you go carbon neutral? Can each of us go carbon neutral? Well, yes, but it's not so easy, right? It's not cost effective quite yet. And what's the future of carbon neutrality? Well, countries and states are trying hard. And you can see that some of them, Denmark and Germany and stuff, are trying harder than others. But it doesn't appear to be impossible, right? They're already reaching neutrality in the best case, which is these good days. It'll take some work till you reach it on an average day. And then from then on, you start to need some technical advances, such as storage, in order to get the carbon footprint down farther. But overall, about 20 years ago, people said this carbon neutrality stuff is completely impossible. No one will ever give up fossil fuels. It's going to be way too expensive. It just couldn't be done. Now you can see that countries are making a pretty serious dent in this. And if somehow people can summon the will to keep working on this, I think there's a good chance that we can reach carbon neutrality, say, in the next couple decades. And so with that, if there's any questions, I'd be happy to answer them. Yeah. Mm-hmm.
Why would they put a solar panel on the top of the building? Why would they put a separate one on the site that these panels didn't?
So the question was, why would they put a solar farm next to the building instead of on top of it? In these cases, which are data centers, they're pretty concentrated. And so the data center doesn't have enough size to generate the amount of solar power. But other people are doing exactly what you said. In particular, the big box retailers, the Targets and Walmarts and stuff like that, they're doing a lot of that because they have 2 advantages. One is they need the power during the day. That's when they need to run their air conditioning. And second, they got these huge big flat roofs, which are not otherwise being used. And the numbers are pretty impressive. Walmart alone has 66 square kilometers of roofs in the United States. 66 square kilometers. And so if they put solar panels on those, even at 10%, that's 6 gigawatts, right? That's 6 nuclear power plants worth during the day when the sun is shining on Walmart roofs. And they do it, the good thing is they do it without government intervention because it saves them money. And so people are doing that, but for data centers, it doesn't work because data centers use power in a too concentrated form. Yeah. Germany does a lot of. Yeah. Mhm.
Always 1960. We know that we can, of course, this is an issue of space pollution. You can put large-scale solar panels in space and beam down in it.
Yeah, that's.
There has been a kind of political issue on that
Yeah.
one because they say, oh, they'll fry the whole
Yeah.
environment. But there has been a series of papers which
Mhm.
prove
Yeah.
that it does not really affect the biological
Right.
features or any of that.
Yeah. So the question is, what about solar panels in space? You can have them up there. They're more efficient because they get light 24 hours a day. The big thing that kills that is just cost. Launching the solar panels is more expensive than you'll ever make back over their lifetime. You need cheaper space travel to make that one work. Technically, it works fine. Now, there's the other worry, of course, is you have this multi-gigawatt beam coming down. It makes a very nice death ray. And so you want to make sure that you're actually aiming it at the antenna and not at, say, the neighbor's city in some country you don't really like. So there's some problems like that. But it's technically feasible, but too expensive at current prices with rockets. That's why they don't do it. I think the number was 300-ish. I'm not sure. I don't know the answer, but it's hundreds, I think, per acre, right? Because you put sort of small, fast-growing trees, the kind they use for paper and stuff like that they grow up to 10 or 20 meters pretty quickly, and they suck as much carbon out of the air as they can while they're doing it. So people have studied which kind of tree works best, of course, and which kind grows where you live.
The cost of solar panels is
Mhm.
dropping very rapidly.
Yeah.
Is that expected to continue or perhaps accelerate as the technology improves? And
Yeah.
what is the estimate of when are we going to get to a 5-year return, say, on investment? That's
Okay.
very attractive.
Well, people have the current projections only produce projections that go out maybe 3 or 4 years, and so they're going down at a pretty good clip, 10% a year or something like that. And so at that rate, to get a factor of 2, you only need 8 years or something like that. And at 8 years, then the 23 years turns into 12 years, assuming they keep the tax credits and stuff like that. And so it's possible. There are obviously people are working on that, but right. There's a whole. I actually have a chart. Let me see if I have that chart here somewhere. There you go. All right. So this is the cost of solar panels versus time. And it's been going down at a pretty good clip. And this is, like you said, this is the actual cost of the actual panels themselves. And you can see that's only a fraction of the total cost. The rest of it's called balance of system cost. And people are putting a lot of work into minimizing that kind of cost to build modules that just plug together with clips instead of having to be wired. That can be built on giant racks rather than having to be individually installed and stuff like that. So people are working on it. People are working hard on it. But this prediction only goes out to 2016 or so. It says right now, commercials at $2 a watt, and it'll be at $1.80 or something in 2 years. So a few percent per year. Question? Mm-hmm. Mm-hmm. Yeah, people have built them like that for there's a solar car competition every year where they do exactly that, but they're not very practical yet. The problem is you can't cover the whole top of the car. And you watch what they do. When they not only park them, they tilt them towards the sun so they get more they get more energy, and they have to build them super light to be able to propel themselves. No, but your car only covers like a half or a third of your parking space. You have the space on the sides and everything. So, yeah. That's a good question. If you cut down the trees, it's coming in at like a 45-degree angle. You'd probably be okay. You have to work out the numbers, but the sun is fairly high in the summer when you get most of your production. So you only need to cut down the sort of triangle of trees in order to get the sun on your solar panel, and you have to figure out how much those trees were absorbing. Just don't burn what you cut down. That's the yeah. Okay. Question?
There is another thing that looking at the price of these solar panels, it takes a lot of time for us to offset. Currently, there is already a certain level of production of shingles.
Uh-huh.
Roof shingles.
Yeah.
Because
Yeah.
solar panel roof shingles.
Right. Yeah.
Why doesn't put the roof thing so that if you work harder on the roof thing, you'll
Mm-hmm.
be more and more efficient?
Mm-hmm.
This unnecessary requirement to offset the cost because you're putting it on top of the roof
Right.
could be
Right.
completely removed.
Right. Yeah, you could remove some of the cost that way. People have thought about that also for windows and facades and stuff like that. Make those solar panels. You still have this problem of the balance of system costs, right? That you still have to wire them, have an inverter and stuff like that. So yeah, yeah. Okay. Question? Mm-hmm. That would be Mark's. Can answer that. It's one common ventilation system. It wasn't. Yeah. There's just not enough room to put in the pipes or whatever. Oh, okay. It's difficult to retrofit it. All right. Yeah. All right. Question? I don't know. This is completely just an academic study. I was talking to Mark about what energy Janelia uses, and I thought it would be an interesting topic, but I have no idea if the trustees have any plans to do anything in this part. So. Yeah. I don't know. I think planting Sullivan's Islands with trees would be cool, right? It's not that expensive. It doesn't ruin the island or anything, so I think that'd be cool. But I don't, as far as I know, there's no consideration.
Yeah, but Lewis, you've neglected the notion of, and then you have to cut them down and bury them.
Right, at 25 years, yeah. Yeah, you get, yeah. Right. And just, well, you just have to take the long view, right? In the million-year view, you're making more fossil fuel. So it's an investment, not a cost. Well, I guess if you eat them, though, the problem is that you turn them into CO2 yourself. So you're burning them. You're just burning them more slowly. So I don't know if that would help that much. Right. Yeah. Question?
Fundamentally, we're addressing the problem again and again. We're replacing one source of energy with another source.
Mm-hmm.
Why are we spending so much amount of energy on like just traveling back and forth for no reason?
That's a yeah.
Are there models that are working like there is no need to travel for unnecessary reasons?
Yeah.
You can telecommute most of the time because of travel.
Mm-hmm. That's an excellent question. The question is, why not just telecommute rather than physical travel? Because travel takes up a third of the budget. And people keep trying that, and I think it is increasing. But people just like meetings, right? They like to travel. They like to, you could telecommute for your vacation to Antarctica or something, and it wouldn't quite be the same. So, all right, thanks very much. See you later. All right, all done.